This is problem 6 of the Operations Research Final by Justin Nathanson. Given here is the problem that we were asked to solve, which is a nonlinear maximization problem subject to a single constraint given below. So for the first way that we were asked to solve this problem was through KKT conditions, or the Karushkin-Tucker conditions. There are 6 Karushkin-Tucker conditions, and for this problem, since there is only one constraint and one optimization problem, resulted in 9 KKT conditions, all of which contain x1, x2, or u1, and the whole goal of this method is to find values for x1, x2, and u1 that satisfy all 9 of the Karushkin-Tucker methods or conditions, and there should only be one of these points. So to do this, we pretty much did trial and error. So the first way we started was to see if u1 was actually equal to 0, which was given in the 3 cases below. By doing this, we found that case 1 was violated through condition number 1 of the KKT conditions. Case 2 didn't work because it violated condition 3. And then case 3 itself didn't work because it violated constraint number 5. So from this, we knew that u1 was greater than 0, and so then we just tried it scenario, case 4, where all the variables were greater than 0. And from this, we were easily able to solve that u1 was equal to 0.5, x1 was equal to 0.75, and x2 was equal to 1.25, which is exciting because these values satisfied all 9 conditions of the KKT method, thus giving us our optimal solution and final answer. Next, we were asked to solve this using a simplex method of some sorts, and to do this, we created a maximization of a z function which contained only the artificial variables z1 and z2. We chose to do this because, and as well as this, we introduced slack variables y1 and y2. This is interesting because the whole point of this would be to find the values of x1, u1, and x2, where the maximization function z was equal to 0, as all artificial variables in a cost, or in this case a z function, should be equal to 0 when we've reached an optimal solution. What's also interesting to note is that by doing it this way, there is an extra constraint that is automatically enforced due to the restrictive entry rule at the very bottom of the screen, which is y1 times x1, y2 times x2, and u1 times v1 is the sum of all 3 of these terms are equal to 0. And so now for part C, we were asked to confirm that the solution we received in part A is in fact correct. And to do this, we just pretty much plugged in x1, x2, and u1 into all 4 of the given constraints, and we were easily able to see that v1 is equal to 0 from the third constraint, and then from the restricted entry rule constraint, we found that it is only satisfied if both y1 and y2 is equal to 0, or y1 is equal to negative 5/3 y2, and from this we were able to see that since it is the restricted entry rule constraint is a sum of 2 terms, all of which are greater than 0, the only way that this is true is if y1 and y2 are equal to 0, and from this we get that z1 and z2 and ultimately the z function we were trying to maximize is equal to 0, which shows us that, in fact, the derived solution we obtained from KKT conditions is, in fact, optimal. So now we actually were asked to solve the given simplex, which I'll flip back to right now. And to do this, we were asked to pretty much just find and confirm that the values for x1, x2, and u1 were, in fact, the ones that we solved for through the KKT conditions. Therefore, to do this, though, we had to pretty much initialize the simplex, as originally the z function only contained artificial variables, and similar to big M method, we don't want that. And to do this, we pretty much added negative row 1 and negative row 2 to row 0, and then stored that value in row 0, giving us the iteration 0 below. And then in iteration 0, we see that both x1, x2, and u1 all have negative 2 coefficients in the z function, and therefore, it really doesn't matter which one we start with in this case, since they all impact the z function with the same weight. So therefore, we chose to start with x1, and in this case, with the ratio test, we found that z1 was kicked out of the basis, and x1 entered it. Moving on from this, we did the same thing for x2 as well as for x1, and we ultimately ended up with the solution where z is equal to 0, x1 is equal to 0.75, u1 is equal to 0.5, and x2 is equal to 1.25, which is in fact correct. One thing to note, though, is that in the actual problem, z does not equal 0. Z would actually be equal to 3.125 or 3.1125. However, in this specific simplex, since we started with the z function only containing artificial variables, z is in fact equal to 0 in this case. So moving on, for part E, we were asked to solve the problem again using dynamic programming. And what's interesting about this dynamic programming problem is that x1 and x2 are not required to, in fact, be integers. And therefore, we had to take partial derivatives. So to do this, we created an f2 star function, which is a function of only x2 and s2, and then we created an f1 star function, which is the z function, original z function that's only a function of x1 plus the f2 star function, evaluated at 2 minus x1. We plugged in 2 minus x1 because that was the singular given constraint of the problem, of the original problem, and thus after taking the partial derivative of f1 star with respect to x1, we were easily able to solve for x1 is equal to 0.75, x2 is equal to 1.25, and thus ultimately z would be equal to 3.125. And then finally, for the last part of this problem, we were asked to confirm this answer in Excel, and this is extremely easy to do in Excel. However, it's important to initialize the problem for x1 and x2. x1 and x2 cannot be empty. Otherwise, this whole solver will not know how to converge, and therefore it will not work. However, the solver function is extremely useful because we were able to select box E2 to a maximization and subject by changing x1 and x2 values subject to the constraint given below, where the sum of x1 and the sum of x2 cannot be greater than 2. Note that x1 is not perfectly 0.75, and that can be attributed to both round-off and truncation error in Excel's solver function. And overall, we have confirmed that to solve this optimization problem, x1 is equal to 0.75, x2 is equal to 1.25, and thus gives a z value of 3.125. Thanks.